So we are talking about minimal spanning trees. That's what we started talking about last time. I will just briefly refresh your memory. If I have a graph, say like this, maybe with an extra little guy in the middle there, another vertex there. What is a spanning tree? A spanning tree is a tree inside this graph which touches all the vertices. And there are typically going to be many ways you can make a spanning tree, but you could do something like, usually I scribble them in. Sometimes I like it better when it's drawn this way. Here is a spanning tree. Something like that. The red part is a spanning tree because it has no loops in it. That's what makes it a tree. And it touches all the vertices of the original graph. That's called a spanning tree. And last time we talked about one method for finding a minimal spanning tree. Minimal in the sense of the weights. This graph that I just drew doesn't have any weights on it. But in real world situations, you want to find a spanning tree with the smallest total distance or total cost or whatever if you have weights on your graph. Something I didn't mention last time, actually, there are methods for finding spanning trees which are inspired by ants. Ant colonies actually create spanning trees, or at least they do sometimes. If you have, say, an ant nest here, and then there's like food here, and here. You know, the ants like to follow each other around, and they lay down like pheromone chemical trails. And if you have ants in a situation like this, they will lay down trails in a way which looks sort of like that, maybe. This is a spanning tree, actually. Ants don't like to go in circles because individual ants, all they can do is follow the trail. They don't actually understand what they're doing, even though all together they seem to be accomplishing goals and whatever. But an individual ant isn't really capable of understanding that. And actually, if an ant trail goes in a loop, the ants will just like walk around the loop forever until they die of starvation or something. You can see there's some cute, I don't know if this is cute, but there's some YouTube videos where someone has like convinced the ants to walk in a circle, and they just walk in a circle forever. But anyway, I'm just trying to say, spanning trees. Ants like to make spanning trees to the extent that they like anything. They don't really understand that they're doing this, but that they do this. And there are actually some very fancy computer algorithms for finding spanning trees that are based on simulation of ant colonies. It's called the ant colony optimization algorithm, if you're interested. But anyway, we're not going to talk about that. We talked about one algorithm last time for finding minimum spanning trees, and that was, so last time we talked about the sorted edges for minimum spanning trees, and this is more commonly referred to as Kruskal's algorithm, but it's hard to remember just that name. Kruskal's algorithm. It's basically the same as the sorted edges that you're going to do, say, on the homework tonight. This time, I want to talk about the other algorithm for doing this that we're going to talk about. Like I said, there are many other algorithms, but the other one that I want to talk about I'm going to call the nearest neighbor for minimal spanning trees. All right? And this is more commonly referred to by some other person's name. This is called Prim's algorithm. I like those two names. No offense to Kruskal and Prim, but I think it's just a lot easier to remember them if you give them more meaningful names. Somebody, I don't know if you noticed, somebody wrote a YouTube comment on the video from last time. I guess disappointed that I only did Kruskal but not Prim. The comment was, Prim slays though. So, I don't know. I thought maybe this is just like a random spam, but a random spam would not reference Prim. I don't know. Somebody actually watched the video and decided to write that. I salute you, YouTube commenter, if you're listening this time. Today's your day. If you're into Prim, that's what we're going to talk about today. Prim's algorithm is basically the same as the nearest neighbor procedure, which you will do on the homework tonight, only for the purposes of finding a spanning tree rather than Hamilton circuit. So there's not a lot to it. I got one example. I got one for you all to try, and I think that'll do it. That'll do it for us today. So I'm going to try and describe how you do nearest neighbor, which is also known as Prim's algorithm. Maybe this commenter was like Prim's grandson or something. Nearest neighbor for minimal spanning trees, all right? On the homework tonight, you're going to do the nearest neighbor for Hamilton circuits. It's the same basic idea, but the mechanics of how you do it is a little different. So the nearest neighbor for Hamilton circuit, remember what that means is you start at a particular vertex, and then you just make choices one after another, and each time you choose the cheapest available edge that actually meets the vertex you're looking at. So the same basic strategy is what we do here. So we choose a starting vertex. This is immediately different from the sorted edges, which does not choose any particular starting point. You just look at all the edges at once and choose the cheapest one. But for nearest neighbor, you choose a starting vertex and you build it from there. So if I ask you to do Prim's algorithm, this nearest neighbor, I would always say something like, use the nearest neighbor to find the minimal spanning tree starting at A or whatever, starting at this particular vertex. And how do you do it? In each step, just like the nearest neighbor, you add on the cheapest option that continues from where you're at that point. So and this looks slightly different for spanning trees, but in each step, choose the cheapest edge that meets the tree so far. So you start off just at a single vertex, and you choose the cheapest edge which meets that vertex. And then after that, you choose the cheapest edge which meets any of the edges that you've chosen so far. All right? This is how you do the nearest neighbor algorithm. And of course, never choose an edge that makes a loop, because we're looking for a spanning tree here. Never choose an edge that makes a loop. But like I said last time, 3 edges meeting is okay. And in fact, usually that's going to happen. 3 edges meeting is okay. In a Hamilton circuit, that's not allowed, but we are not talking about Hamilton circuits. We're talking about spanning trees, which generally speaking, a spanning tree will have 3 edges that meet at the same vertex. Like here, this red one, you can tell. There are several times when it did that. All right, this is how we do it. I got one example. Actually, I thought we'd just do the same example. I don't know if anybody cares. This is the same example, but this is the example that I said was about like my light up garden gnomes or something. All right, and here's the outlet down here. And each of the edges on this graph represent places where you might connect them together using electrical wires. And I want to connect up all the wires in the cheapest way possible. Cheapest meaning using the smallest distance of wiring. And I will tell you all the distances. That one is a 10, up top is a 5 and a 4, across here is a 6 and a 4 and an 8, over here is a 13, here's a 12, and at the bottom is a 20. All right, so I'll say find the minimum spanning tree using the nearest neighbor, Prim's algorithm for the folks at home, starting at the outlet. That's what we're going to do. All right, so remember the idea of the nearest neighbor. You start wherever you're starting, and I just tell you where to start. And then from there, you choose the cheapest option as you go. So from the outlet, oh, I didn't put a number here. This diagonal I didn't label. Is a 7. This one right here is a 7. And actually, that's the first edge that I'm going to choose for my spanning tree. You start by looking at the outlet, What's the cheapest edge available? My options are the 10, the 7, or the 20, and I'm going to go with the 7 because that's the cheapest. All right. Notice this is immediately different from what would have happened if you were using sorted edges. Sorted edges, you look at all the edges at once and choose the cheapest one overall, which would be the 2 4s. So this is a different process. I'm going to try and do a little narration here. So from the outlet, the cheapest is 7. So I'm going to choose the 7, right? Now we look at all of the edges that are touching the tree that we've made so far. It's not much of a tree, but this is what we've got so far, this edge. And now I look at all the edges which touch this edge, and I ask myself, what's my next cheapest option? It could be something from the outlet, or it could be something from this one, because I'm just looking at all the edges which touch that part that we got so far. Which one is it? The 4, yes, she's showing me the fingers. The 4 is the next one. So now, the cheapest, I'm trying to narrate here, just because when I just write the answer, it's hard to tell how I got that, because I'm just scribbling. But I'm going to say, first, from the outlet, the cheapest is the 7. And now, the cheapest, which touches the tree so far, which is not much at this point, is the 4. So I pick this 4, the vertical 4. All right, that's my next choice. It's the cheapest one which touches the edges which I've picked so far. And you just continue like this. What's my next choice going to be? I see some more fingers. The other 4, yeah. Right now, this 4 is now the cheapest edge overall, which is touching the ones that I already picked. So next, oops. The other 4. So that's here. What will be next? Again, the cheapest edge touching the ones I've already done. I think it's the 5 at this point, right? I'll just write down sort of in order here. I might ask you to do this, by the way, on the test or on the homework or something. Just write down the list as you choose them, just because, like I said, if all you do is show me your answer, it's not clear at all to me how you actually got that. So I'm trying to indicate my steps a little bit. What happens after the 5? You look at the cheapest edge, which touches the ones already. That will be the 6, but I'm not going to choose the 6 because that would make a loop right here. So the 6 is off limits. Next would be this 8. Also, I'm skipping the 8 because that would make a loop right here in this triangle. So I'm going to say this. Skip the 6 and 8 because they make loops. The next would be this 10, but again, the 10 also would make a loop if I used it here. So skip the 10. Next would be 12, and I think this 12 actually does, it is legal to take the 12. It doesn't make any loops. So I take the 12. And now actually I'm done at this point because everything, every vertex is being touched by the chosen edges. So skip the 10. Use the 12, and it's done. All right, this is how we do the nearest neighbor for spanning trees. The result is something that looks kind of like that. That's actually the same answer. I don't know if you remember this. We did this example last time with the sorted edges procedure, and we got the same answer here, the same shaped spanning tree. All right, that typically will happen. So let me just say some words here. Like the sorted edges that we did last time, from last time, the nearest neighbor is guaranteed to give you the best spanning tree. This is much better than the nearest neighbor and sorted edges for Hamilton circuits, which do not always give you the best answer. The best answer is super hard to find in a Hamilton circuit. But for the minimum spanning tree, they both actually are guaranteed to give you the best answer. And what that means, if you think about it, is basically they're both usually going to give you the same answer, because each one is finding the best answer, which is going to be the same both times, the best answer. The only way that they would give you different answers is if there were ties and you just had to choose at random between like two edges with the same number on them. So if there are no ties, and even if there are ties, it's still usually going to be the case. If there are no ties, the nearest neighbor and the sorted edges will give the same answer. They're just two different ways of finding the same answer. Because of this, on the homework, you'll see on the next week's homework and on the final exam, when I ask you questions about this, I'm likely to ask you to give me some kind of description like this, so that I can tell if you're actually doing the one or the other. If I say do this using the sorted edges, if you just show me the answer, actually I won't be able to know how you did it, because you will get the same answer regardless of which method you used. So that's a little something to keep in mind. All right, let's just do one. I got this this example. I hope that you brought back the paper that I handed out last time. If not, I brought some more. If you weren't here last time, I would like you to try that same graph. Hopefully you have more blank ones on the paper. See if you can find the minimal spanning tree, and I would like you to start you have to start somewhere, right? So let's do this starting at the edge in the upper left. This one, all right? So let's find the minimal spanning tree using nearest neighbor, starting right there. All right, anybody else need the paper? Good with the paper? If you do it right, you should get the same answer that you got from last time. Coloring the cheapest one, which touches the ones that you write. So you can't then use that. That's why I have 16. Can we talk about these? It looks like people are doing just fine. You start over here, and I am going to looking at this vertex here, I have three options: the 30, the 60, or the 52. I choose the 30 because that's the cheapest one. And then maybe I'll put like a little numbers to indicate that was my first choice, just in case when you look back at your notes, if all you see is the answer, there's no clue about how you got it, unfortunately. What should my next choice be? I look at all the edges which touch this edge. That would be 52, 60, 50, or 62. I choose the 50. So that's my second choice. Next, I am looking at all the edges which touch any of these ones so far. I think the cheapest overall from those would be the 16 here. And so I fill in the 16. That was my third choice. What's the next cheapest? Somebody shout it out. The 15, yeah, right here. That's the cheapest edge now of all the ones touching the ones I've got so far, is the 15. That's the nearest neighbor. So that was my fourth choice, was the 15. What next? Yeah, next I believe is the 14 right here. It looks like I'm just drawing sort of a one stretched out path, but it's not always going to be that way. Next I choose the 14. That was the fifth one that I picked. My next lowest number available would be 18, but that's going to make a circuit, so don't use 18. I believe it's got to be the 19 now, right? Are you feeling good about this? Yes. Next comes the 19. That was edge number 6. And then you have to try to look carefully and find the cheapest available edge, which is next to one of the other ones you've already picked. I think it's the 20 this time, right? That was my 7th choice. And then it looks like the 24. That was my 8th choice. Am I doing all right so far? I think so. Then the only vertices left are these two I got to get. I think I would take the 31. The 30 here is going to make a circuit, so I don't want that. 31 and then the 31 should do it, I think. So this is my choice number 9, choice number 10. All right? Any questions about that one? This is how we do the nearest neighbor algorithm, also known as Prim's algorithm, for finding minimal spanning trees. All right, and I think that's all.